This is Lecture 1A for Calculus 1, Introduction to Functions. In this lecture, I'll give some definitions, especially definitions of functions. Then I'll give a list of unforgivable errors. Surely, if you see them here, you will never commit them again in your whole entire life. The first definition is that of calculus. Like, what is calculus? The most basic definition is that it is any system of calculation using a symbolic manipulation. So if you take logic and you see predicate calculus, or you're studying databases and they talk about relational calculus, you'll know what they're talking about is their scheme for manipulating the symbols of logic or the symbols of databases. If you're in medicine, there is a whole other definition for calculus, as in renal calculi, and those are kidney stones. For this class, we study differential calculus, and then in the last chapters of this class, we'll study integration. The differential is the rates of change. The integrals are calculations of areas and volumes. All this is called calculus, often without the qualifiers of differential and integral. Another definition is the title of the book. It's called Calculus Early Transcendentals. The transcendentals is a name for the group of functions that are not linear and not algebraic. These are your exponentials, logs, trigs, and hyperbolic functions. Those are the elementary transcendental functions. Early means that the transcendental functions will be introduced early in the book, early in the class. This means we will not develop all of calculus for polynomials and then go back and develop all of calculus for exponentials and trigs. We will just start and pull all the functions along as we go. In this particular class, this is Math 200, Calculus 1, we are restricted to real valued functions. You will not see any imaginary numbers or any complex values here. Okay. It's also single variable calculus. What this means is that single variable, you'll say, well, there's always two variables. There's an x and a y. But single variable means there's only one x. There is only one independent variable. For example, if you are talking about the position of an object, you might call the function of that object s. And it would depend, as it shows here, on the three spatial variables for the three space where we live, x, y, and z, and it would also depend on time. This is 4 independent variables. In this class, we cannot consider such a complete definition or complete function of the position of an object. We have to restrict to one variable. For example, we could say that the position depends on time, s of t, or that the position depends on one spatial variable, s of x. The focus of this class follows Stewart's report of the first recommendation of the Toronto 86 Conference on Teaching Calculus, and that is focus on conceptual understanding. I know that sounds like a bunch of educator talk, but truly the key to understanding is the concepts. Once you have the concepts, all kind of doors open and things get very easy. But to get the concepts, you have to slow down. And I think the basic key to learning the concepts is that of observation. To observe in math, you ask yourself questions like, what would happen if? What would happen if x was 0? What would happen if I took the inverse? What would happen if I sketched this graph in a different way? Graphs are very important. Look at graphs. Look at as many graphs as you can. Draw the graphs. Drawing really helps. It helps because your hands are another pair of eyes. And for some of us who don't see that well anyway, and for those of us who are dyslexic, drawing the hands are actually better than the eyes that we have. And don't worry about any labels like dyslexia. I take that as a sign or symptom of genius. That's a joke. Many people are dyslexic. It's no big deal. Just start using your hands instead of your eyes, and things will get better. And remember, too, if you're in engineering, the first thing you do is make a sketch. Sometimes when you make that sketch, the problem is half solved. Maybe it's all the way solved as soon as you see the sketch. What is the opposite of observing? Here's the opposite, and it's done frequently in math classes. You do a zillion problems that you do not understand, hoping that somewhere along the line understanding will come in. It usually doesn't. And then, after you do these problems, you get the answer book out, or look in the back of the book, you find what the answer is. Then you go back and patch up your problems. That is absolutely the opposite of conceptual understanding. But I'm sure you know all that. So now I'm going to move on to the definition of a function, and I'll approach it in two ways. One is a conversational approach that you probably are used to from your algebra classes. And then the other approach will be a precise definition. So in the conversational approach, we start with the intuition that you might have. We start with, for example, two sets of anything, of numbers, data, information, any two sets. Each set we name with a variable, for example, x and y. Then we establish a correspondence so that the values in one set depend on the other. For example, the paycheck depends on the hours worked. The paycheck is the dependent variable, often called y, and it depends on the independent variable, which here I called x. What I described before was a relation between two variables, or two sets. A function is a special type of relation in which each value of the independent variable is associated with only one value of the dependent variable. Of course, graphically, you're used to finding functions by seeing if they pass the vertical line test. As soon as you start talking about functions, you start talking about the domain of functions. Ideally, and in a standard, typically, and you should write the function, put a comma, and state the domain. That is the standard mathematical way of defining the function. But in these a lot of preliminary algebra courses, that's not even bothered with. They just write the function, and you either are to understand the domain or figure it out. I have a little formula here that sometimes helps in finding those domains. Start with the idea for these real valued functions that the domain is all real values. Then look at restrictions. There are two types of restrictions. One is restrictions due to the application. Say you are selling certain objects. You cannot sell negative amounts of objects, so if x is the number sold, x cannot be negative. In fact, you might restrict x to the non-negative integers, because you can't sell half an object even. On the other hand, if you're selling real estate, you could sell any amount of acreage, so in that case, x might be all non-negative real numbers. So those would be restrictions due to your application. Then there are mathematical restrictions, and they fall into two main categories. One is you cannot divide by 0, and the second is you cannot take an even root of a negative number. That means the square root, the fourth root, the sixth root. If you do, the answer will be, or what you will end up with, is an imaginary number, and because these are real valued functions, that is not allowed. So here's the formula. First, say that the domain is all the real numbers. You can just do this in your head. And here are the math symbols for all real numbers. I encourage you to use math symbols. It's less writing, and they're good symbols. Upside down block A, if you don't know it, means all, for all. And then the R is, of course, the real numbers, either script or sometimes it's block with an extra vertical line. So in your mind, you're saying it is all the real numbers. Then look for any possibility to divide by 0 and throw those numbers out. Okay, so you have to throw out all the numbers, and those will be single numbers, individual numbers that you'll be throwing out. You might have to factor the denominator. On the other hand, if there's no denominator in the problem, there is no problem with step 2. You can just move on to step 3. Now you look for any possibility to take a square or any even root of a negative number. When you find those restrictions will be complete intervals. You'll end up throwing whole intervals out of the domain. What's left over is the domain. So here's an example. Let's consider the function f of x, which is equal to the square root of x minus 2 over x minus 4. So in our minds, we say the domain is all real numbers. Then we say, is there any possibility to divide by 0? Yes, there is. If x is 4, we will be dividing by 0, so you throw x out of the domain. You can see that happened right here. Find the highlighter. And so x just got thrown out of the domain. Now you say, is there any possibility to take the even root of a negative number? And up here, you can see that that is an issue. If x is less than 2, you will be trying to take the square root of a negative number. So all the numbers less than 2, all that interval, has to be removed from the domain. What's left over is the domain of the function f. You can write it in either of two ways. You should be able to write it correctly both ways. Here is set builder notation. The domain of f equals, and then you have these curly brackets, and you start with x. naming the variable. X is an element of the real numbers. You don't have to write that part so much because, well, these are all real valued functions and of real values. So, but X, this part means X is all X that are elements of the real numbers, and the vertical line means such that X is greater than or equal to 2. Remember, you can take the square root of 0. So X has to be greater than or equal to 2, and X cannot be 4. The other way to write it is an interval notation. You should understand, again, both of these. Here is the intervals of the real, for example, on the real number line that constitute the domain of F. We start at 2, square bracket means include 2. 2 is included, and we go to 4, write that with the parentheses, set union, start again at 4 with an open parentheses. This way we go from 2 to 4, jump over 4. This just jumps over the number 4 and goes on to infinity and close with a parentheses. Plus and minus infinity are always closed with parentheses, not square brackets, because they are not numbers that can be included. Now here are the precise mathematical definitions. For those of you who are very mathematically inclined, you might not like to read a lot of words. You'd rather have things very condensed, and in reading this you can say, why didn't somebody just say this in the first place? So I'm giving you 2 definitions. Here's the first one. Let x and y be sets. A function from x into y is a subset f of x cross y. This means the Cartesian product of x and y. You might not know Cartesian product, but you know the Cartesian coordinate system. It's the same thing. You have the x and y are placed orthogonal to each other, but instead of a coordinate system, a graphing scheme, this means the abstract idea of x cross y. So f is a subset of the Cartesian product of x and y, such that for every element in x, there is exactly one element, y and y, such that that pair is an element of f. The set x is called the domain of the function. The set y is called the codomain of the function. The subset, that means all the y's that are in f, the subset of the codomain is called the image of the function. Now, most of the algebra classes use the word range. Other math classes will use codomain and image. Image is a subset of the codomain. Here's a second definition. A function is defined by 2 sets x and y and a rule f. Okay, I want to highlight that. So you've got 2 sets, x and y, and now you've got the rule. The function is considered a rule, which assigns to each element in x precisely one element in y. The set x is called the domain of the function, and y the codomain. If x is in x, the image of x is that element in y which the rule associates with x. And here's how you define the image. Okay. Again, these are very precise. They don't require any intuition on your part, but they do require that you study and learn a vocabulary. Here's some notation for functions that you might run across. The one you're familiar with is y equals f of x. In other words, f of x is another name for y. If the relation is also a function, it gets the name f of x. Here's another, which f is a mapping from x into y. This is a similar statement here. And then this, with the arrow with the vertical bar before it, shows that x is associated with y. Okay. Those are just different notations you might run across sometimes. I want you to have seen them. Okay, now I'll go through a list of unforgivable errors. Unforgivable in the sense that the entire problem might be marked wrong if you have one of these errors. If you commit a sign error somewhere in the middle of a problem, that's usually a reminder. But these errors are more serious. Most of these came off of the UAF website, and there's some other websites that list them. So it's not just me that thinks of these errors fairly serious. The first set here reflect a lack of understanding of operations involving binomials or polynomials. In these cases, you needed to FOIL. A plus b squared is not a squared plus b squared. You have to FOIL. The second error here, the second group of errors shown here, is canceling unilaterally. You cannot cancel these x's and leave the 2 alone. This is really 2 problems. It is x squared, but the second part should be 2 over x to be correct. So those are considered pretty bad problems. These errors are just due to a total understanding of fractions, and those are pretty bad errors. Hopefully you have never done these, or you did them so far in the past that you never even think about doing them right now. Of course, you need common denominators for fractions. Okay. This error is more just forgetfulness or sloppiness. There are rules for logarithms, and whoops, you need to, okay, the log of x times y is broken out as log of x plus log of y. So review the rules for logarithms if you don't know those already. The next error, there are a lot of trig formulas and trig identities. I don't expect you to have memorized all of them. What you need to know is that you have to look them up. Multiple angles, half angles, sine of x plus y, that's just not the sine of x plus the sine of y. There are formulas that govern that, and identities, and you have to look those up. Again, you're not expected to memorize them, just know that they exist and know that you have to look them up. This error has to do with exponents. The scope of an exponent is a number right before it, or if it's in parentheses, it's everything in the parentheses. Since the minus sign was not in parentheses, the square only goes with the x. The answer is not x squared, but really it's minus x squared. On the other hand, if you had minus x in parentheses squared, then you end up with x squared. Okay. How about negative exponents? This is not true. X to the minus 3 equals 1 over x cubed. When you move from numerator to denominator, the exponent comes along and changes the sign. So if you would have made this error, review exponents. X to the minus 3 is defined to be 1 over x cubed. The minus sign has nothing to do with x. This error represents a lack of understanding of what sign is. Here's the rule. Function names are usually one letter long, like f or g or h, except for functions that have long names. And the functions that have long names are sine, cosine, tangent, cotangent, secant, log, hyperbolic tangent. They're functions. They could have just as well been written with the letter f. Then what comes after them is really in parentheses. But a lot of times we don't write the parentheses. We write sine x. But the x is really the argument of sine. So you cannot cancel those x's. And the problem here isn't necessarily the canceling as much as not understanding that sine is a long name for a function. This error has to do with a quirk in math notation. Most of the time math notation is consistent, it's precise, it's very well thought out. However, when it comes to the inverse of a function, f to the minus 1 does not equal 1 over f. However, with numbers or variables, it does. With functions, f to the minus 1 means the inverse of x. In this case, sine to minus 1x is the arc sine of x. Right? It means the inverse. I'll talk about that in another lecture. But this is a quirk in the notation of math. When it's a variable, when it's a number, a negative exponent means you can move it to the denominator or vice versa, and the negative exponent will become a positive exponent. With functions, sine to the minus 1, tangent to the minus 1, f to the minus 1 in general means the inverse function. If you want to write 1 over f of x or 1 over sine x, you have to put sine x completely in parentheses and put the negative 1 sign way on the outside. So if you had any problems with those two errors, or if you would like to investigate a little bit more of these precise definitions, I'll give you 2 online references. One that has very good explanations and discussions, and it uses a conversational approach, is purplemath.com. it starts with your intuition, and it builds on experiences or examples from life, and then builds on that to reach mathematics. planetmath.org is an online reference, or online, like a small encyclopedia of precise mathematical definitions and statements. If you want to use that, you have to work at learning what all the words are. They're not all written out and explained to you. You have to learn the vocabulary. The other problem with Planet Math is that their indexing scheme is a little confusing. I have a hard time just typing in something in the search and finding what I want. Maybe you'll have better luck than I do, but I had a little trouble with their approach. Both of these approaches are valid ways to learn math, and both have problems. The problem with the conceptual way of learning things, the conversational way of learning things, is that your intuition may not be sufficient for you to learn the ideas of math. It might bring you just so far, and then you're left with this big gap. How do I understand that in view of what I used to know? Maybe there is no way. So there's this gap that can happen with this conversational approach. The other approach, you have to spend a lot of time learning definitions, learning words, and it's going to be very terse, very concise. So what can I say? There's no free lunch, or I guess you could say pick your poison, whichever way you want to look at it.